Now, guys, we're gonna be looking at the sum of subspaces. So we are given this theorem. We have the theorem. They say, let me write it. The theorem. For the theorem, they say that if W1 and W2 are subspaces, if W1 and W2 are subspaces of V, then W1 plus W2 is also a subspace of V. Right. So now we're given to prove this. So if we try to break this down, we realize that actually we have, this is the hypothesis. This is the hypothesis. And this is the conclusion. It means that we are required to assume first, if I come to prove, we are required to suppose that W1 and W2 are subspaces of V, meaning that they have a zero vector, they satisfy scalar multiplication, and they both satisfy vector addition. Right. So since we have this, we can define this. Since we need to show it that it is also a vector space, we can define this by saying we can define W1 plus W2 by W1 W2 such that this will be W1 being an element of W1, W2 in an element of W2. So we define this. And remember I said that first we need to show that this is a vector space. So it means that first I need to show that I need to show or check, first I need to check if the zero vector is found in the W1 plus W2. So this is the first thing that I'm going to check. So the question is, how do we check this? So remember we are given that W1 and W2 are subspaces of V. So I can use that. I can say since W1 and W2 are subspaces. What does it mean when we say that they are subspaces? Are subspaces. What we mean is that already zero vector is found in W1 and zero vector is found in W2. You see, right? So since this is the case, we can say so if I take zero vector plus zero vector, if I take the two zero vectors, obviously I'm going to find a zero vector. You see, right? It means that this is found also in W1 plus W2. Don't forget this is from W1 plus W2. So we found that a zero vector is found there. So after checking the zero vector, we can now check closure under addition. Right. Then for us to check closure under addition, we are going to use this which we have defined. I'm just going to pick two elements. One element, let me just pick two elements from this instead of saying one element. But from the elements which I'm going to pick, the first one will always belong to W1. The second one will always belong to W2. So I'm just going to use this. I'm just going to forget about W1 and W2 for now. be in subspaces. Now I'm going to use this to show that if I pick two elements from this set, those two elements will also be found there. So first, I'm going to remember I said that before you use this definition, you must pick two elements from this, right? A term we're dealing with V. We used to say let U, V be an element of that. So I'm going to let U, V be an element of W1 plus W2. You see, right? Then, after having this, or I can say such that each of these U will be defined from this and V will be defined from that. So we can say such that U is equal to, can even take it like this, or just take it like this, such that U is equal to W1 plus W2. You see right now, such that U will be equal to this, where W1 is an element of W1 and W2 is an element of W2 according to this definition. You see right now. And now I take V to be W1 prime plus W2 prime. Where we know that W1 prime will be an element of W1 and W2 prime will be an element of W2. So since I picked these, I can say now that I can add them. Yes, right. So I pick these, mean that I can add them. So I can check now. If I take U, trying to check if there is the addition gonna be in W1 plus W2. So this is W1 plus W2 plus 1 plus W2 prime prime. So this will be, I can just take these ones, W1, W1. I only want the ones that will be in W1. Here I want the ones that will be in W2 only. So I'm just going to take the ones that are in W1. I know it's these ones which are in W1, so I must add them together. W1 prime plus W2 plus W2 prime. So since now I've added this, we know that we can give a conclusion to say that since W1, we can give a conclusion to say that since W1 and W2 are subspaces, we know that if I take their subspaces, I add them, I'll find that you see, right, since they are subspaces, I know if I take two elements from this, I'll find that their addition is a satisfying closure. And if I take two elements from W2, I'll find that they also satisfy closure. You see, right? So this simply means that this will imply, or it will tell us that U plus V is an element of W1 plus W2, because this is an element of W1, element of W2. So which will be this case. Right. So now what we need to check, if scalar multiplication is satisfied. So we need to check closure under scalar multiplication. So for us to check this, we need a vector. We're going to need a vector. We're going to need u, which will be an element of W1 plus W2. I said that if we take a vector from this and which take C as any scalar, and then the multiplication, and then actually I think I need to define, let me just state what is u. Actually u, we know that it's W1 plus W2, such that W1 is an element of W1, such that W2 is an element of W2. So I know that if I take C, U, this will be equal to C W1 plus W2. This will be equal to C W1 plus C W2. You see, right? So now we know again that since W1 and W2 are subspaces, we will have that say W1 will be an element of W1, and we know that closure is a closure under scalar multiplication is satisfied from this, right? Will be an element of W2. So if this is the case, this will imply that Cu is an element of W1 plus W2. Now, since we see that everything has been satisfied, we can now say hence W1 plus W2 is a subspaces. The subspace of V. You see, right?